Hi class, welcome back to Sholey Physics. Today is brought to you by the one ring to rule them all. Oh yeah, gotta love when that onion ring is stuck in the fries. So anyway, today we're going to be covering resistance and resistivity of a conductor. Yesterday, or last lesson, we looked at current and introduced current, electrical current, and drift velocity of electrons. So today we're going to think about, we're going to look into how electrons actually move through in a current and why some materials might have a different number of particles per unit volume, and that affects this quantity called resistance and also the property of that conductor called resistivity. So to start off with something hopefully that's on the familiar side from yesterday, current, we left off defining it as the number of particles, charges per unit volume, times the amount of charge, the quantity, usually the elementary charge. 1.6 times 10 to the negative 19 is the elementary charge for an electron. And we have the drift velocity and the area. All right, so that's in the scope of looking at a section of a conductor and taking a little slice out of it. Let's make a little slice here. All right, so we're thinking about the charges, the electrons, as they pass through that little slice. All right, next. Something you might have read about in your chapter is a quantity called, it's nothing that we're going to be using except for in this discussion, but it's called the current density. And it's right here in this expression. If we divide both sides by A, by the area, then we get the current per size of the area. Okay, so it's the density of the current within that little pepperoni slice. I said it again. Darn it. Didn't mean to. I was really trying to avoid the pepperoni again today. But current per area. So if you just think about all the charges within that little slice as they pass through, if they're drifting through here, some drift velocity, that's the current density. How densely packed are those charges in that little slice? And we're just going to use the letter J to represent that current density. Current density. Okay. So keep that in mind that current density is NQVD. Now that becomes less important now. I just wanted to pull that little piece out. Now just as a piece to remember, the number of charges, number of electrons per unit volume in copper is 8.5 times 10 to the 28 particles or charges per cubic meter. That's kind of blurry there. I'm going to work on that writing. Anyhow, or at least the view of it. So where are we going to go next? Well, as you think about how charge might pass through here, through that little section or that little slice, do you think temperature has any bearing? You might recall from chemistry a concept called thermal expansion, that temperature affects the spacing of atoms or molecules. As you raise the temperature, what happens is that matter tends to expand. Those particles are moving faster and faster. There's more space between those particles, therefore. So do you think that's going to have a bearing on how well charge passes through the material? The answer is yes. So the material itself, how well it conducts, what it's made of, the number of valence electrons, the electronegativity, all these factors go into how well electrons can pass through that material. So they feed into the property of that material. And just as temperature affects density, temperature also affects resistivity. And so that's a new concept I want to introduce. Resistivity is defined by the electric field per the current density. Okay, so let's think about that little ratio there. This is a lesson full of ratios, but in the end, that's what we're really focusing on. We're not going to worry with memorizing or working with all these ratios, but let's talk about them still, you're smart people. This ratio shows us how the electric field, how strong that is in the material compared to its current density. So a strong electric field, if you raise it higher and higher and higher, that should also increase the current density. A stronger electric field will motivate those charges to move faster or move more. With a higher electric field, there's going to be a greater electric force. So therefore, you can see as E increases, J will also increase proportionally. The greater the electric field, the greater the current density. So we get this ratio of electric field to current density. So now let's think about the fact that, let's say, aluminum and copper may have a different resistivity, a different rho to them. And so which one do you think is better, copper or aluminum? If you just did a lesson, you might realize that copper probably has a lower resistivity than aluminum. Copper is a slightly better conductor, which makes it gives it a lesser resistance or resistivity to it. So charge may travel better given a particular electric field through copper than it does through aluminum. So aluminum's J value is probably lower. There, I have to get this right. If J is lower, that makes the resistivity higher, which means copper has a higher current per unit area. It can pack more charge in to that slice. All right. So moving on, thinking about resistivity as a function of temperature, what do you think will happen if we increase the temperature of a material? Just like density, the resistivity will change as well. Now, if you increase temperature, matter expands, but it also becomes faster. So faster moving matter, faster moving atoms will tend to make it more difficult for those electrons to progress through that piece of matter. So higher the temperature should mean higher resistivity, or you could also say lower the conductivity. But we're focusing on the resistivity for the time being. So usually this is a temperature dependent value here. So there's going to be kind of a base value. Now this isn't a constant here. This is the resistivity. This rho naught represents the resistivity at a starting or a reference temperature. Now I'll call that reference temperature T naught. Okay? Now I'm not done yet. So if we don't change the temperature of the material, the resistivity won't change either. So we're going to start with a 1 plus. And now every material, copper, aluminum, any other metal you can think of, will react differently to a change in temperature, just as the density would. So there is a measurable temperature coefficient of resistivity called alpha. I'll describe that here. This is called the temperature coefficient of resistivity. Okay, alpha. And that's multiplied by a change in temperature. All right, so a comparison between the temperature now, temperature that we change it to, and that original reference temperature, or whatever that rho naught is, that original resistivity before we change the temperature. So this is a way to define the value of resistivity given a reference. So if we have a starting resistivity at a particular temperature, then if we raise or lower the temperature, we could determine the new resistivity. You're going to be able to get a little bit of practice with that. Okay, so there we kind of end part one. How well charge moves through a material is affected by its resistivity, the resistivity of the material. Now, part 2 here, I'm going to move on. I'm going to have to come back to that in a moment. Let's think about how do the dimensions of a conductor itself. So we just talked about what the material is made of, or the medium of the conductor. But I didn't really speak about size. What do you think will happen if we increase the length of a conductor, or even that cross-sectional area? As we see here, those are the two main dimensional pieces here. We have the length, and there might be a radius in here, giving us kind of a radius of this slice. So there's an area to this as well, length and an area to this conductor, cross-sectional area. So that's what I mean. How do the dimensions of a conductor come into play? So let's go back just a little bit. We're going to go back to, here we go, just our last piece. This definition of resistivity and how it relates to the electric field. Okay, electric field is a couple of units ago, so let's bring that back in and unpack it a little bit. We got E, there, I did it again. I repeated my church pastor's expression. It's just getting into me. I don't want that to be in me. We're not going to unpack it. We're just going to look at it. Okay. Don't you hate when that happens? People say things all the time and just starts to get into your speech. All right. So what I've done is just rearrange this. Electric field equals rho times the what is that called? The current density J. And here we're going to transform that current density and forget about it from here on. So you might also recall that the current density is current over cross-sectional area. So we're trying to bring the dimensions of the wire into this. That's the reason I'm doing this. So rho times I over A. Okay, so we just got rid of that current density. Yes. All right, so now let's start thinking about how that electric field and the current and the area all are mixing in here. So I'm going to make a new sketch. Bring it down here. Okay, so there's our segment of conductor once again. And let's define it. It has a length, capital L. It has a cross-sectional area, A. All right. Now if we're to take an electron and move it. Now, let me rephrase that. Let's take an electric field applied within this conductor. There's the electric field. Going from left to right. Oh, it's going from left to right. So I really should change this. If this is an electron, then it's going to move opposite that electric field. Okay, so it's going to move from right to left. That actually doesn't matter too much. But what does matter is that to move it from right to left, it's going to take some work. And this might be the surprising thing. In our previous chapter, we talked a lot about how the potential difference between one point on a conductor and another is 0. And well, that's approximately true. When it comes to circuits, it doesn't really work as an approximation. You see, for really, really long wires, there's going to be a lot of resistance, and it takes a lot of work to move an electron over a long distance. Historically, that's one of the reasons why Nikola Tesla's idea for alternating current won out above Edison's idea for direct current. In that competition is a good rap battle of history on that one. You should check that out. It does have some words in it that, get a little rough. But anyway, with alternating current, the idea is an electron just moves back and forth almost in place, and that pushes and pulls the electrons in the whole transmission line from the power plant to your house. That pushes and pulls those electrons just kind of back and forth in place. Well, as with direct current, we're trying to move an electron over miles and miles of distance. So there's this incredible amount of resistance to that. So using alternating current, it reduces resistance, the energy loss. It reduces the work done in moving that electron and transmitting that energy. So it's a much more efficient type of electrical transmission process. But getting back to it, we are dealing with a wire here, and there's a small, very, very small, near zero but non-zero amount of work done, which is significant when we're talking about a wire, where it is insignificant when we're talking about just like a sphere or a spherical surface. So there is a tiny bit of work done to do this, and it usually comes out in the form of heat. It tends to heat up the wire. When you turn a circuit on, it heats up the wire. So work is done, vibrates those molecules, and that actually in itself changes the resistivity of the wire. We'll see some effects of that later on in the course. So, long speech over. To move an electron from here to here, there's an electric field applied, and it's a constant electric field. So the potential difference between one point and another, VAB, will be electric field times the distance. You might recall that, V equals ED. All right. Very similar for moving an electron in a capacitor, so between two plates. You might recall that. Now in this case, if we move an electron from one side of the conductor to another, we've moved it the distance of the length of the wire. So we now have V equals EL. All right, or we can transform that, because we want to try to basically get rid of the E here. We want to move it out of the picture, get rid of the electric field. We want this in terms of the dimensions of the wire. So this is going to pull in the length into our discussion, V over L. Okay, so now let's take that, substitute it up here, set it equal to this rho I over A, and what do we get? We get V over L equals rho I divided by A. Okay, now let's take the electrical quantities, put them together, and put all the dimensional quantities together, and the properties of the wire together on one side. Length is a property of the wire, rho, the resistivity, is a property of the wire, and A, the cross-sectional area, is a property of the wire. So I'm going to transform this just algebraically, bring the L up to the top, and I down to the bottom, and we get V over I equals rho L over A. Okay, so a ratio of the potential difference from one side of the conductor to the current passing through the conductor is related to the resistivity of the wire, the length, and inversely proportional to the cross-sectional area. So this ratio here is what we call resistance. The resistance of the wire. It is dependent on the resistivity of the wire, the length, and the cross-sectional area. So our last piece here, since R is proportional to, I'll put that up here, so resistance. All right. So if resistance is proportional to rho and L divided by A, if we do change the temperature of the wire, that's not going to change the length or the area significantly. Now we might have some thermal expansion, so yes, A may increase a little bit, L may increase just a tiny little bit. Usually they're not very visually apparent, so there may be a tiny effect on the cross-sectional area and the length of the wire, but the greater impact is going to be on the resistivity. So if we look at this, if we increase the temperature, the length and the area remain approximately the same. They actually both might expand proportionally, and so that doesn't affect things anyway. So if rho is a function of temperature also, then in addition, resistance is a function of temperature, and we can write that temperature dependence like this as well. Instead of rho, we can use R. 1 plus alpha T minus T0. So that's just a little offshoot result of all this. But mainly, here's our big guy. Okay, Resistance is rho, length over area. That's the end of my notes presentation. All this information, or all these notes relating to voltage and current, you just keep this in mind as you try out the homework tonight. That'll really help you out. So I hope that this has been helpful. And oh dang, I just repeated Mr. Anderson, didn't I? There was a Mr. Anderson video there that you just watched, but told you, repeating stuff. But hey guys, I miss you all. I gotta stop saying that. Choking myself up. Grab yourself some onion rings and fries, but don't go out. I don't know how that works, but hope you're doing well. Take care.